Testing, testing. Can you hear it? Works okay. Hmm? Yes.
Okay, I'm just
And so are we. Yes.
Okay, because it says
Yeah, that hasn't
Trellis and
changed.
it's down.
Uh,
Maybe it wasn't updated last year.
okay.
But I'm updating it now.
Okay. Well, you can double check. Just email Steve Gordon, but I'm pretty sure it's Stampede.
Your slides you put up on your website, right?
They're all there?
You're all there? Okay. Just want to make sure. Difficult to keep up with the PowerPoint.
Yes. So welcome back, everybody. So does Marquita have any comments she wants to make on the website and all the logistics? Because last time I gave you a pointer to the list of 4 forms we were asking you to fill out for 2 supercomputer accounts and a survey and all of that kind of good stuff. And if you have any questions about it, this is a good time. Marquita?
Right, so keep thinking of questions if you have some. We have 54 students signed up for NERSC accounts right now, and I want to remind you, if you have a NERSC account, still fill out that form so we can add you to the repository. And we have 66 students on Piazza, so if you haven't done that, please join the discussion. Other than that, there are no reminders. There was one question about what languages you might need to know for this class. C is the language we'll be using in all of the homeworks, so some good knowledge and experience of that will be very helpful to you. If you would like to try learning it on the fly with the course, that we'll leave that open to you, and there's a link to a self-paced course on the website homepage if you want to try that.
Okay, thank you. Anything else? So the door is open back there. It's just a little noisy. So last time I gave an introduction, and I got to all but one slide, which is a rough list of topics for the curriculum this semester. So I'm going to start today with 1.5 lectures where I'm going to do a deep dive into computer architecture. And for the rest of the semester, we're going to work at a much higher level of abstraction, but you should know where all the time really goes, and for that, this 1.5 lectures on where what happens at the bottom is going to be important. Then we are going to spend some time on parallel programming models in machines, so that means how do you actually write the software. And we're going to start with shared memory, so p-threads and multi-threading. That's OpenMP, which is what runs on your multi-core laptops. Then we'll go up to the big distributed memory machines like Edison and that you're going to be doing your homework on, and how they send messages to one another. And then there's sort of higher level data parallelism, and that means, for example, AVX instructions on your multi-core laptop. It also means GPUs, but now of course there are even more interesting processors like Intel Xeon Phi, where it also lets you do many operations at the same time on 2 arrays of data. And then there's cloud computing, which is yet another architecture that people like to use. So those are going to be the models in machines, and the languages that we'll be using to program some of them. And some of these you'll have homeworks on, and some of them it's all fair game for your final class project, are shared memory, so p-threads and OpenMP in the shared memory world, MPI for distributed memory. And then there are going to be a lot of other languages and frameworks that we're going to expose you to, because there's no just one way that people like to program these things. So UPC, Unified Parallel C, you'll have an assignment there. and which lets you program on distributed memory but makes it feel like shared memory. And then CUDA is for GPUs, but that's getting replaced by something that's a little bit more parallel across different architectures, not just NVIDIA. Spark was invented here. There's now a startup. It's how a lot of people do cloud computing, and so we'll have a lecture on that as well. And then there are a lot of higher level languages or DSLs, domain-specific languages people have built for scientific computing. PETSI is just one of many, and so we'll give you some exposure to those too. So the thing that we're going to also talk about is the 7 dwarfs that I mentioned last time, the fact that most scientific computations, in fact a lot of commercial ones, can be broken down into just these 7 standard patterns that appear over and over again. And sometimes that means somebody's already built them into a library and all you need to do is find the right one, but some of them aren't quite so simple and you have to do it yourself, but there's sort of standard ways of going about parallelizing them, and so we'll talk about those. And those come from scientific computing, and then there were these 6 additional ones that came from taking apart a lot of non-science applications. And so that you see them there, graph algorithms, graphical models, and so forth. And because of the length of the semester, we're really only going to give you a deep dive into graph algorithms. So, how do you deal with large graphs? Because that's one of the most popular ones. So then there's some other general techniques that apply to all these different programming problems. So auto-tuning. How do you automatically search a whole bunch of different implementations? Because it's very hard to just look at it and see if it's the best one. So people write code generators that automatically search for the best implementations. Load balancing, so I mentioned that last time, that's the bottleneck, making sure all of the different processors have an equal amount of work to do. And then performance tools, in which we'll also have a special lecture, because figuring out where the bottlenecks are is very tedious sometimes, so people have built a lot of tools for that. And we'll have a lot of special lectures on those applications. So any questions? So the motivation for the next 1.5 lectures, this sort of deep dive, is the fact that most applications, even just on a single processor, forget parallelism, are running at less than 10% of the peak performance of the machine. And peak is what the manufacturer advertises, that you can't possibly go faster than that. And so what that means is that before you worry about running it in parallel, you should worry about the fact that you're only getting 10% of the performance on one processor, and by putting some effort there and going, there's a factor of 10 you might be able to get, or if not, you should know why you can't get it. And that's something you should worry about before you go on to the next harder stage of making it run in parallel. And it turns out that a lot of this performance is lost in the memory system, because that, as I mentioned last time, is the bottleneck. It takes a lot more time to move data than it takes time to do the arithmetic. And so we're going to talk in some detail about how to reorganize algorithms to minimize that cost. But we do need to look under the hood and know exactly where the time goes. And so let me talk about the conclusions you could draw from today's lecture. One is that computer architectures are really fascinating, and I'm going to show you these really, really simple programs, and if you tweak them just a little bit, their performance changes completely. And I really want to know why simple programs can behave in such complex ways. Some of you might draw that conclusion. You might also like to draw the conclusion, I'd really like to hide all that. I'd like to learn how to design algorithms so they behave well no matter what complicated stuff lies underneath the surface. And you might also say that I hope somebody else worries about that for me. I just want to know how to find the best tools that automatically run as fast as possible, and I don't have to worry about any of that stuff. I mean, I know somebody has to worry about it, but I want somebody else to do it. And any of those are perfectly reasonable. And at different points in your career or during the course, you may have different attitudes toward all these things. And but today we're going to dive down to the bottom. The data is complicated, and as a scientist, I have to show you the data so you can draw the right conclusions from it. So here's the outline of today's talk. I'm going to talk about sort of the idealized model you might have for how much a program costs to run, and then tell you about the actual cost. Then I'll go into more detail on the memory hierarchies and where the time goes as you move the data inside just a single processor between DRAM and different levels of cache. I'll also give you a little exposure to parallelism inside a single processor, because as I said before, some of that parallelism, even in one processor, is done for you automatically. Some of it's been done for a long time. And then I'll start doing a case study, which is matrix multiply, and talk about how all these ideas can be used to make matrix multiply go a lot faster. And in fact, I'm going to tell you about some lower bounds a theorem which says that no matter how you organize your classical matrix multiply, there's a lower bound on how much data has to move inside your computer. And then, given that lower bound, we'll talk about algorithms that actually attain it. So let's start with the idealized and actual. So this is terminology that should be familiar. Let me just make sure we're all on the same page. So a processor has names for everything in its address space. So they're bytes or words, and these are represent integers, floating point numbers, pointers, or arrays. So that's what an address points to. And the operations that you do on them include reading and writing of that stuff from the main memory into fast objects called registers. And you're only allowed to do arithmetic and logic, the real work, on stuff that's sitting inside those registers. So the order in which you do these is, of course, specified by your program. And so what the compiler's job is to take an instruction that you write in your code, like A equals B plus C, and translate it into these lower level operations, which is what we have to understand so we know where the cost goes. So suppose you write A equals B plus C. Then what does that turn into? The compiler knows the address of variable B. It's stored somewhere in memory. So it says, please go to that address and bring it into register 1, which is sitting inside the processor. It has to be there to do any work on it. It goes to the memory and reads wherever C is addressed and brings that into register 2. Then it can finally do the actual work of the addition. It sums it and puts the answer in register 3. And when it's done, it knows where the answer is supposed to go, and it writes that register out to address A. And everything is executed sequentially in that order. Again, this is the idealized model that we should think about. And so the cost assumes that, okay, I have 4 instructions. Each one runs in, let's call it 1 cycle. And so this costs me 4 cycles. So in the real world, so now we have to sort of make that a little bit more realistic. You have not just these registers and main memory, you have registers and caches. And so a cache is a small amount of memory, but it's much bigger than the registers, much smaller than your big memory, but it's close to the registers. And so what you do is you keep all of the stuff in there temporarily while you read it back and forth into the registers so that you can reuse it over and over again. And that saves you the time of going to main memory. And I think I had this analogy last time. So if you're trying to write something, you're sitting at a desk and you need a pencil, you first look at the top of your desk and grab a pencil from there. That corresponds to the registers. If it's not there, you go open a desk drawer and pull out a box of pencils. That's your cache. And if it's not there, you have to walk down the hall. That's going to DRAM to get a bigger box of pencils. So it's that sort of analogy. And different memory operations can have very, very different costs. Then there's parallelism, which even in a single processor is there. You may be able to do multiple additions or multiplications at the same time, and the hardware will try to do that for you. And so depending on the order in which you write your code, if you have 4 independent multiplies in a row, the compiler will try to recognize that and say, oh, I can do 4 things at the same time. But if you write it differently, it may not be able to do that. And there's something else which is called pipelining, which, because most of these instructions can be broken into phases, and just like you have an assembly line which can do many things at the same time in a factory, you have an assembly line, a pipeline in a computer where all the instructions are broken up into pieces so they can be overlapped. So in principle, you may ask, why is this my problem? Why doesn't the hardware and the compilers do all of this for me? And people are trying to improve hardware and compilers all the time to look at your code and automatically reorganize it so that all of this is taken into account. So in theory, they should work perfectly well, but in practice, they don't always do that. And so it goes back to this old quote, there's, in theory, there's no difference in between theory and practice, but in practice there is. And the oldest attribution of this I could find was to Yogi Berra. It probably goes back to Aristotle. Anyway, so now, given that motivation, we're going to go look at memory hierarchies. And so there are going to be 3 topics on how we use memory hierarchies to go faster. The first one is we want to keep the stuff local. We want to keep the data close to the processor. And so we can keep it either close in time or space. So temporal and spatial. So there are going to be 2 ideas that we use. And then I'll talk about the basics of how the caches work. And then I will show you some really crazy data that's measured by running incredibly simple programs on real processors. And I'll show you how long it takes. And then we'll look at this crazy data and we will reverse engineer the actual architecture of the machines to figure out what it looks like underneath that causes this strange performance. So here's what the memory hierarchies look like. And so, as I said, there are two kinds of things to take advantage of: spatial locality and temporal locality. So what does spatial mean? Spatial means if you grab a word from memory because your program needs it, you're probably going to use the stuff right next to it in memory. So imagine you're accessing a matrix and you're reading a row and you get one entry, you're probably going to want the next entry in the row and the next entry in the row. And the hardware will imagine that's true automatically. And it's going to grab not just the one entry you ask for, it'll grab all, a whole bunch of other entries in the same row of the matrix. And so you should write your program to take advantage of the fact that grabbing one grabs a whole bunch. That's spatial locality. And the other one is temporal. And that means when the hardware brings the data into cache, it's going to keep it there for a while, and it's going to assume you're going to use it over and over again. And so, so you better do that. You should reuse it as often as possible. So of course the cache is small. Eventually it's going to fill up. What does the hardware do? It asks, what's the least recently used thing in this cache? And it throws that away. And so you should write your programs knowing that's what the hardware is going to do. And so here's a picture of just to give you some orders of magnitude of the costs at different levels of the hardware. So this is where the work actually gets done. So there are registers, and there's wires connecting all the registers, and then this is the thing that actually executes the instructions. And then if you want to get some data that it's not in a register, you go to cache, and that's maybe of size kilobytes, and it takes, let's say, order 1 nanosecond to get to that. So that's pretty fast. If it's not there, you might go to the second level cache. And depending on your architecture, that may be on the same chip or it may be off chip. But let's say that's about 10 times as slow to get to that, but it may be 1,000 times larger. We're talking about megabytes. Now, if it doesn't fit on, and some chips have L1 cache, L2 cache, L3 cache. This is kind of a cartoon. But eventually you go to main memory, and that is, let's call it gigabytes. But that's another factor of 10 slower to go off and get that. I'll have real data in a little while. If it's not there, you may go to disk, where we're talking milliseconds and terabytes. And if you're at NERSC and your data doesn't fit on disk, there's a robot. And what the robot does is it goes to this big room where there are a bunch of tapes where your data has been recorded. It goes and grabs the tapes and puts it on a tape reader, and you get your data. And that could take a long time. Okay? So, but there are all these different levels. And then there's cloud computing, right, where we're going over the internet to get your stuff. And there's actually a new technology that was that's been around for a little while. We actually have all of it in our cell phones. It's called flash memory. And so the thing about flash that's going to be new here is that reading and writing have very, very different costs. There's a factor of 10 difference. It's 10 times more expensive to write to that memory than to read from it. And people are talking about not just putting it in your cell phones, but putting it in these big computers as well. And so when we're beginning to ask ourselves, how do we design algorithms when reads and writes have these very, very asymmetric costs? And so all of this is part of the design process. And in fact, yes, Intel and Micron just announced a new technology called 3D crosspoint. And so that's going to be very, very widely distributed in all our laptops in the foreseeable future. They haven't published the details, so I can't say much more than that. So let me just remind you of Moore's law, which I talked about last time, which says that transistors are getting smaller. This hasn't quite ended yet, although this is quite old data. And so that's great. What does Moore's law mean for memory? It's getting faster too, but if you ask how long does it take to get to DRAM and bring it back on the chip, that's not getting faster very much at all. It's only getting 7% faster. So that means that even today, if your program is not memory bound by going to DRAM, it may be next year or the year after that. And so you might ask, well, why is there this big difference? Why it's because the physics is actually different. Because to go to DRAM, you have to go off chip. You have to charge up a pin on the side of the chip, which then has to pump a bunch of electrons to another chip to get to the DRAM. And that's subject to different physical limits than moving data just on the very much smaller wires that are on one chip. And so that's why that's improving much, much more slowly. And we just have to live with that. So that latency, the time it takes to get to DRAM and to get back, as I mentioned before, we're going to worry about temporal locality. So we're going to make sure that we reuse data that we've brought in over and over again. So if it's close in time, it'll be there. And then we're also going to get data, not just one word. We're going to grab a whole bunch of it at one time because you usually access contiguous words in memory. And that actually is growing at a different improvement rate. because there's these two different measures of how fast hardware goes that I'll define more carefully later. There's the latency and there's the bandwidth. So let me speak by analogy to a freeway. So let's talk about the latency and the bandwidth of I-80 between Berkeley and, say, Sacramento. So the latency is how long it takes to drive from Berkeley to Sacramento. And that's, the distance divided by the speed limit, okay? Now, what's the bandwidth of I-80? That's how many cars per hour you can pump through the freeway from Berkeley to I-80. So that depends on the speed. It depends on how close together the cars are. And it depends how many lanes there are. It doesn't depend on how far apart Berkeley and Sacramento are. So those two ideas, bandwidth and latency, show up in electronics too. How many bits per second you can pump and how long it takes to actually get there. And so, and those are governed, they have different physical limits. And in fact, the last slide, this was the latency. That's only getting better at 7% a year. But the bandwidth is getting better at 23% a year. So that's getting better faster. And so we should make sure we take advantage of that. And the way that's done is by grabbing not just one word, but a bunch of contiguous words and bringing them into the cache. And so that process is better, and we should take advantage of that. That's spatial locality. And so the other thing that's good about this is that when you issue this instruction that says, please get a whole bunch of words, that can be overlapped with the arithmetic. And so we have parallelism between the memory operations and the arithmetic. And the other interesting thing is that in order to take advantage of this, the hardware kind of spies on your program. And it says, all right, I'm looking at your history. Which words have you accessed? Can I guess which ones you want next? And it does a sort of machine learning at a very low level in the hardware to actually predict what your next address is that you're going to want to load in. And so it's sort of spying on you. I mean, we know the hardware spies in this anyway. But this is to our benefit, we hope, by trying to grab the next word, and with high probability, you'll want to use it. Okay, so, and I'll show you some benchmarks that sort of measure how well hardware does this. So now let me go down one more level and talk about how caches really work. How does it decide what to, where to store the data? And so let's imagine to just keep it really simple, that all my addresses are just 9 bits long, so I can just draw everything. Of course, there'll be 32 or 64 in the real world. So suppose I want to read in data from memory, and this is its address. Where do I put it? The simplest thing to do is just throw away the first 5 bits, look at the last 4, and if I have a 16-word cache, this tells me where to put it. Those 4 bits tell me where to put it in the 16-word cache. So it'll be stored there. So that would be a direct access. And so now, what does my hardware do? I say, please load location something, something, something 1101. It goes to the cache and says, are you there? And to do that, it needs to, of course, remember what bits it's stored there, because there's a whole bunch of different words that could be stored there. And if it's there, it says, great, you can have it. It's a cache hit, and it's very fast. Otherwise, it's a miss, and it has to go off to the next level of, to DRAM or the next level of cache and actually get that and bring it back in. That's slow. That's called a cache miss. Now, this is sort of assuming that the cache, one thing is stored at a time, but remember I told you about spatial locality. I'm going to grab not just one word, but a whole bunch of contiguous words. So let's suppose that you ask for location 1100. What the hardware might do is grab not just that word, but its neighbor, and they'll read them both in. And so if you read either one of these, it'll grab them both and bring them into your cache and store them in 2 consecutive words. So it'll be available to you. And how many words it grabs is called the line length. And we will reverse engineer the line length from the various benchmarks that I show you. The other quantity is called associativity. And this simple example I had up here was, this is stored in one location. And so if I read another word in that also ends in 1101, I have to throw that out. Only one word fits. And that has problems. So suppose, for example, I have a matrix, and it's stored row-wise, and I want to read in a column. Okay, and let's suppose it's a 16 by 16 matrix, and I'm reading it down a column. Then what's the address of different entries in the same column? They differ by 16. So they'll all end in the same 4 bits. And so they'll all map to the same location in cache. And so reading down that column, I'll have cache misses all the time. And I don't like that, right? I'd like to be able to read my matrix row-wise or column-wise. And so what people do is they have associativity. They're willing to have not just one location one address ending in 1101 stored there, but you can have n of them. And so, for example, if I had n2 or 4, I could have 4 words ending with 1101. And that's yet another design space. So all of these are parameters that hardware manufacturers choose differently when they build their computers, and it affects your performance. Okay, so right, so those are the basics of cache. So why do we have multiple levels of cache? And instead of just having one big one, it's because it's too expensive to build one that runs as fast as possible, because it has to be very, very close to the registers, right? And so it's the same analogy as having your tabletop, your desk drawer, and going down the hall to a cabinet to get a pencil. And so if we want to have a very large cache, it'll take too long and take up too much space and too many bits. And so people are tuning this all the time. How many levels of cache, how big they should be, and historically they kept adding more and more levels. But occasionally they took out a level because they decided it wasn't worth it. And so here, 2 historical examples just for fun. Cray is the company that builds Edison that you're going to be using, and they kept adding levels. But at some point, this is a historical supercomputer, they eliminated one level because they realized that a lot of the programs had a lot of misses. And so they knew they had to go to DRAM anyway. And so they had so many levels of cache that going from registers to L1, oh, it's missing. Then it went to L2, oh, it's missing. Then it went to L3, oh, it's missing. There were so many levels it slowed down the common case when everything was in DRAM. So they threw out a level so they could get to the DRAM faster. And that depends on your application mix. That's what they chose to do. And IBM uses something called a victim cache. And so when you throw something out of L1, it just doesn't throw it away completely so that the next time you use it, you have to go to DRAM. It keeps it somewhere else for a little while. And a victim cache is sort of a temporary little L2. And in case you want to use it again soon, it will go there first and check to see if it's there. So there are all these attempts to guess what you're doing to go a little bit faster. And there are other levels in the memory hierarchy. And let me just mention one because it's going to show up in the benchmarks, something called the translation look-aside buffer, or TLB. So the way computers work is that they want you to be able to run programs that are so big they don't fit in DRAM, and they don't want you to worry about that. So what do? If it doesn't fit, you put it on disk. And whenever you access a word that's not in your memory, it actually goes to the disk for you automatically to go get it. That's called virtual memory. And so there's a table which is in the memory, hidden to you, which keeps track of which part of the memory is on disk and which part is really in DRAM. And so that's called this translation look-aside buffer. And so we're going to see that showing up in the benchmarks in a moment. Okay, so now, having given you all that complexity, I'm sure you want to see what the data looks like. So here is the really, really simple benchmark that we're going to run to see what impact this has. This is called a micro benchmark because it's just like 2 lines of code. And the simplest thing you could imagine doing is have an array of length L, and all I'm going to do is read it. I'll read A0, A1, A2, A3. That's the benchmark. And so I'm going to time this loop and run it many times. I'm just going to loop from 0 to L minus 1 and load A sub I, which in this case is a 4-byte object. So, and I'm going to do that many times in average because it's, if it's not in the cache originally, I want to so-called warm up the cache to make sure it's there. So that's going to be the simplest experiment, just count how long that takes. But then I'm going to vary that experiment as follows. Instead of accessing consecutive words, I'm going to access every second word, every fourth word, every eighth word, and the distance between consecutive locations is called the stride, or S. So I'm going to do this sort of 2-dimensional family of experiments. It's going to depend on the total length, and it's going to depend on the stride. And so I'm going to show you some pictures of how long it takes as a function of both the length L and the stride S. And we'll see some very interesting arrangements here. And as I mentioned before, if you have a matrix which is stored row-wise and you read a row, that's what you're doing. But if you read down a column, then this is the more appropriate sort of model of what you're doing, skipping various words. Okay, so now before I show you the data, let's try to have a mental model so we know what to expect. And so that when we look at it, we can say, oh, I know why it looks like this. So what I'm going to do is plot the data this way. I'm going to have one line of data for each value of L, so for the length. And then, but I'm going to read that with stride 1, stride 2, stride 4, stride 8. And so the horizontal axis on my plot is going to be the stride. And the vertical axis is going to be the time per word. So down is good. And so I'm going to draw it this way. And a small stride is going to be best. And so let me just draw this picture here. So if everything fits in L1, what we expect is that the first time I read it, it'll all go in L1. And every time I read it after that, and I'm going to do it many times in average, it should take the same amount of time. It should just give me the L1 access. And it shouldn't matter whether once it's in L1, whether I get consecutive values or every second value or every third value. So I'm kind of hoping that when I do this experiment, I'm going to see a straight line at the bottom that's going to be down there as long as the total size is less than L1. Now, what happens if I get bigger than L1? And that's going to be the cache hit time. So I claim that we should expect something that looks like this. So let's ask ourselves why it should look like that. So here, let's suppose I'm right here. So I read in a word, it's not in cache. But then once I read it, I bring in, say, 4 words, if the cache line is 4, then the next 3 are already in cache, and they'll be fast. So the first one, the first word, that costs a DRAM access. And the next 3 are cheaper because they're already in cache. But now, if I only read every half word, the first one is in, the first one costs the main memory access. The next one is free. But then I have to go to main memory again. So the cost is going to roughly double. And it's going to keep going up until I get to this corner. So what do you think the horizontal coordinate of that corner is? What should that tell me? That's going to be the cache line length. That says I read in 4 words, and I only use one of them. So every time I access something, I have to go to main memory. And so if the stride is bigger than the cache line length, I'm going to be up here. So that's what it should read me out. And so that should be the memory time. So that flat line is the time to go, well, to the next level of the cache. So why does it start going down again? Not really. So the question is, was it aliasing? I don't think so. So remember, for each one of these curves, L is fixed, but my stride is changing. So how many words do I access in total? L divided by S is the inner loop is accessing. So suppose L divided by S gets small enough that everything fits in L1 again. Then at this point, it's going to start decreasing because everything is actually fitting in L1. So that's going to be the pattern. So now, let me show, so this is what we should mentally expect. Let me show you some real data, and let's try to reverse engineer the architecture. Okay, so this is now an old machine, and it's old enough that, this simple model captures everything that this does. And you can see I've run the experiment many different times. There's many different curves here, starting from 4 kilobytes all the way up to 64 megabytes, the yellow line. And the time's on the vertical axis, and it goes all the way from 396 down to 6. So there's a factor of 66 difference between having L1 and going to memory. So a factor of 66 is something that we want to capture. We don't, before we worry about parallelism, get the factor of 66. And then the strides start at 4, 8, 16, 64, and so forth. So that's the horizontal axis. So each one of these dots here represents an experiment. And so maybe the first observation is that this is complicated. And that, so ultimately what this is going to motivate us to do, I mean, we're going to go do every detail right now, but at the end of this lecture, what we're going to have is a simple mental model. What we need is a simple model of what this means so that when you write your code, you can say, yes, I'm going to be in this range, not in that range. Okay. So that's going to be one of the goals. So let us look at the bottom and work our way up there. So if I look at the bottom, all these lines that are down there, those correspond to 4 kilobytes, and because it's hard to read, I put it here, 4 kilobytes, 8 kilobytes, and 16 kilobytes. And so all of those run at full speed, which is to say 6 cycles. And so that tells us that the L1 cache size is 16 kilobytes. And if you look up the hardware speed, that's actually 2 cycles exactly. So that's what all those numbers at the bottom tell us. Okay, so the next bunch of lines, which are these ones here, so that corresponds to the lines 32 up to 1 megabyte. And so that's what we think the, and then, when we get to 2 megabytes, it starts going up again. So that tells us there's another level of cache, which is the L2 cache, and it runs at 12 cycles, or 36 nanoseconds. Okay, so that's the next level of the memory hierarchy. Let's see here. So, and then finally, we get to the top, and that's the 132 cycles, and that is 396 nanoseconds, and so that's what we expect the main memory. So we see there are 3 levels of memory hierarchy here. So the next question, so that was pretty easy to read off. So now, let's look at these various corners and see what we can deduce from that. So the first thing to notice is that when we don't fit in L1, but we fit in L2, then we go up to this corner, and then it flattens out. And so as I suggested before, that tells us what the L1 line size is. And up here, every one of these hits, only gets 1 word per line, and it happens here at 16. So that tells us the L1 line size is 16 bytes. That tells us the L2 line size is 64 bytes. Before every time we get something from L2 cache, we only, so we read a whole line of 64 words, but we only use one of them, and then we go to main memory again. So that tells us what the L2 cache line size is. So there's one other sort of funny thing going on here, which is, what is this? So this, we thought this was L2, but it's sort of going up. Okay. I claim that's a translation look-aside buffer. Because what happens here is that, remember, what the machine has to do is ask, are you in main memory or not? Or are you really on disk? And that it does that by looking it up in a special table. And so what happens when that table fills up, right? That's yet another hidden level of the memory hierarchy. That means that I have to go refill up that translation look-aside buffer. And by doing the analysis, you can decide that the size of one object that is kept in cache, that is kept in main memory, is 8 kilobytes. So that means what the machine does is it decides, am I going to keep, is it going to disk or is it coming into main memory? It's going to do very large chunks of data to decide that, and it's going to be 8 kilobytes. And that can be read off from here, and it turns out there's actually 32 pages. And that happens right when that number is 8K pages times 32 entries. And so all of that can be read off in excruciating detail from this particular architecture. Okay, so this I did in maybe more detail than you care about. But the point was to show you what real programs behave like. And now I'm just going to show you some more recent machines very quickly as eye candy to show you they're even more complicated. And so here was an experiment done a little bit later on a predecessor of Edison at LBL called Seaborg. And here are the various numbers plotted here that we should be able to read off: the L1 size, the L2 size, main memory, and so forth, but it's obviously a lot more complicated. And just one more example, which was an Intel Core 2 Duo, which is even more recent. And just to tell you one story related to this picture, I think I told you about the Parlab, where we had this funding from Intel and Microsoft to work on parallelism. And so we had a retreat a few years ago, and a student was putting up, I think, this plot or one very much like it during the poster session. And because this is sort of still standard way you analyze how memory hierarchies work. And by the end of the poster session, there were 5 Intel engineers standing in front of the poster arguing about why it looked like that. They couldn't agree. And they all had their laptops out showing one another spreadsheets that were under NDA, so we couldn't look at them, trying to say, this part of the hardware makes this corner happen. So this is still an open research area, how to interpret all of this stuff. And so it says that it's interesting research if you want to think about hardware at that level. And it also motivates us to have a much simpler mental model going forward when we design our software, so that we're operating down here rather than up there. Okay, so any questions about these pictures before? Yes, microphone? Marquita?
Can you explain why it goes back down again?
So yes, the reason it goes back down is that the experiment is I have L words of data, but I'm accessing them in step sizes of S. So the total number of words that I'm reading is L divided by S. And when S gets large enough, L divided by S is small enough that it fits in cache again. And so it starts behaving as though all the data fit in cache, even though the original length certainly didn't. And that's why you have this behavior that it goes down again, that I motivated here. But that's sort of, I was mostly analyzing what was going on here, and not exactly where that corner was.
Are you making some assumption on the layout of the data?
So the question is, am I making some assumption in the layout of the data? And the answer is yes, it is contiguous. And the first experiment at this point, when S equals 1, I am assuming they're absolutely contiguous memory locations. When S equals 2, I'm skipping every other one, so the address is increment by 2 and so forth. So that is precisely the experiment, which I'm now going to generalize, actually. So if I have an array which is laid out row-wise, say, and I read a row, it's precisely this example. Now let's suppose that it is a 16 by 16 matrix, and I read it down a column. Then every entry is going to be 16 apart. So it's good. The stride will be 16, right? So you would pick that particular point on the axis to figure out what it was. So it depends on your matrix layout. Now I'm going to have another slide later that talk about these different possible matrix layouts. There's a lot of them, but that's the simplest way to think about it. Right, so this will influence your algorithm, right? Do you access the matrix row-wise or column-wise? It depends on how it's laid out in memory. Any other questions? So here's one more example just to show you how hard the hardware is trying to guess what you want to do next. And this is actually motivated by your question about accessing a matrix. So this is just a very slightly more complicated benchmark. And so now here's the pattern. It depends on two parameters, L and K. I'm going to read L contiguous entries, and then I'm going to skip K and read L more. So in the matrix example, suppose that I have a 16 by 16 matrix. I'm going to read it, it's stored row-wise. I'm going to read it row-wise, but I only want to read the leading. All right, let's say it's a 7 by 7 matrix, and I want to read the first 4 by 4 submatrix. So I'll read the first 4 entries, skip the rest of the first row, read the first 4 entries of the second row, skip the rest of the second row, and that's what the pattern looks like. And accessing a submatrix is a perfectly common thing that people do all the time. So let's time this and see how well that works. And so the point is that I mentioned before, the hardware is running these very simple machine learning algorithms in the hardware to guess your pattern, right? So the idea is that you do this for a long time, and the hardware should show, I know what you want. I'm going to go get it ahead of time. And the question is, how well does the hardware actually do that? So let me show you some experimental data. And so what we have here, this is for a particular value of L and S. And the total length of it, which is how long it takes for the hardware to is on the horizontal axis. So this is L, the horizontal axis. S is fixed. And then the vertical axis is gigabytes per second, so the speed of access, so up is good. And there's a whole bunch of there's 4 different hardware platforms here, so I'm comparing different hardware platforms. And I ran 2 different experiments in each hardware platform. And so if we take the top line, that's Nitanium, an old dead Intel machine, but I'll show you that. So what is the horizontal line? That's where you just access consecutive locations. You don't skip anything. And so that's the absolute peak speed that the hardware can go at, and it's running, at somewhere close to 4 gigabytes per second. This red line is how fast you go when you read, 128, 256, 512 words, and then you skip something. Eventually, it learns that, and it gets close to the peak speed, but it takes a long time for it to learn that pattern. And so it's doing a tiny, it's doing 1/4 or less of the peak speed of the machine, because because it's not smart enough to learn that. Now, this other machine, the Intel Pentium 3, that's the P3 down here, it learns right away, but it's also running much more slowly, right? So there's no penalty for skipping, but the whole machine is rather more slow. And then this is an IBM G5, and an AMD Opteron, and you can see it all takes them different lengths of time to learn this pattern. And so this is all changing over time as the hardware improves, but this is the kind of stuff you can expect as well. Okay, so the reason, question?
Yeah, so at least looking at it, the stanza length increases, so wouldn't that just mean that you have longer contiguous accesses to memory?
Right, but if that's all that impacted the performance, then all these curves would be identical. They would all be curving up to the sort of the same hyperbola approaching the horizontal line. But you can see that something happens here. It learns something. So the hardware is actually doing something more clever inside to realize that there's this pattern.
Okay, thank you.
Okay, good question. Any other questions? So the reasons that I've dived down into all this detail is not because every one of you cares about that level of detail, but that's the real data, right? As scientists, got to show you the real data, and then we have to decide what to do about it. And so the goal going forward is to have a simpler mental model so that when we write our algorithms, it will accommodate this behavior and it'll run fast without us having to do this level of benchmarking all the time. So the point is slight changes in the architecture of the program can change the performance a lot. I didn't change it. Those benchmarks were all very similar. LNS only changed a little bit, and I got this big variation, a factor of 66 in the performance. And so here's the technique that we're now going to use, that we'll use later in the lecture to deal with this. It's going to be called blocking or tiling. It's going to be a general technique to take your program and make sure that you're accessing consecutive memory locations as much as possible so that we're as close to the peak as possible. And then the hardware will do as well as it can, but you will have given the hardware as many hints and opportunities as possible by using this algorithmic technique. And it's basically divide and conquer on your data structure. And so we will see how to do that. And I'll use matrix multiply as the illustration. Okay, so very good. So the next thing I want to tell you a little bit about is parallelism within a single processor, and then we'll get to the matrix multiply example. So I mentioned pipelining, and so here is an example which you've all experienced, I'm sure, which is doing your laundry. And so rather than using an assembly line in a factory, let's talk about how a laundromat works. And so there's a washer that takes 30 minutes, a dryer that takes 40 minutes, and folding that takes 20 minutes. And if only one person were allowed in the laundromat at a time, if you weren't allowed to do pipelining, then it would take 30 plus 40 plus 20 minutes, or 90 minutes to do your laundry, and the next person would take 90, and the next person would take 90, and that's obviously a waste of time, and nobody uses laundromats that way. And so instead, if you have 4 people, what you do is you pack it together as tightly as possible, and since the dryer is the bottleneck, the dryer runs continuously all the time, and so the total time for 4 people is 30 plus 4 dryer operations plus 20 minutes at the end for the last folding, and everything runs in parallel. And so here's the terminology to describe this phenomenon, whether it's hardware or a laundromat. So the sequential time would be one person laundromat at a time. It would be 6 hours, 4 times 90 minutes. But the pipelined execution, which is shown here, is the dryer runs 4 times continuously. You have a 30-minute startup and a 20-minute cool down at the end, so 3.5 hours. The bandwidth that now we can define it carefully is the number of loads per hour that you can do. And without pipelining, that's 4 loads in 6 hours, so it's 4/6 loads per hour. But if I use pipelining, it's 4 loads in 3.5 hours, and that's much, much better. So now, since I'm, of course, interested in not just 4, but as many piping as much stuff through my pipeline as possible, so 100 people show up, what's the limit on the bandwidth? And so the limit is going to be the dryer, right? And so it's basically going to cost me 40 minutes per load, except for the beginning and the end. So it's 4 divided by 40 minutes, which turns into 1.5 loads per hour when you do the math. And so that is the bandwidth limit of this particular thing if you keep the pipeline filled up all the time. Now that doesn't help an individual, but an individual still takes 90 minutes from the time they walk into the laundromat to the time they walk out. That's the latency, right? That's the total delay for any one operation. But the bandwidth can be much, much better than that. And so the bandwidth, as I've shown here, is limited by the dryer, by the slowest pipeline stage. So ideally, all these pipelines would have exactly the same length. And if in that case, what's the potential speed up? It's the number of stages, right? If all of these took the same and there are 3 stages, you can go 3 times faster. And so the more stages, the better, as long as they all take about the same time. So that's a laundromat. Now let's look at a computer. And so here is what happens inside a very simple computer, which is taught to all 61C students. It's the MIPS data path. And every instruction is broken up into 5 stages, so in order to make things run as fast as possible. So the first thing you have to do is go fetch the instruction from memory. So that's the first stage of the pipeline. The next one is you have to take that instruction apart and figure out what it's telling you to do. So you have to decode it and then go get the data from the registers. If it's telling you to add register R1 to R2, that's the second stage of the pipeline. The third one actually executes the pipeline, and it computes, and it may also compute an address. If the instruction says load or store, you need to compute the memory location. So that either one happens in parallel. The fourth stage is going to memory. If it's a read or a write, that's when that happens. And then the fifth stage is called a write back, because what that does, if the output is updating a register, it may be the next instruction needs that data, right? If you're computing a sum, you keep updating the same register, you got to put that sum back into where it belongs, and so there's a data path there. So if all were perfect, this would go 5 times faster. But of course, accessing memory is a lot slower than executing the instruction, so it's not perfect. But not every instruction uses every one of these stages of the pipeline. But this is how the hardware works. And this is actually, there's pipelining not just at this level, but there's pipelining inside these boxes. That box there that's called the ALU, Arithmetic Logic Unit. So that's where the actual arithmetic happens. And as I mentioned before, that can be broken up into pieces, because when you take 2 64-bit numbers and add them, there's a lot of things that you can do in parallel, and that's broken up into a stage. And so, for example, a floating point multiply, which is done inside here, it may take 10 cycles total. But it may have, but if you break that up into stages, it still can, the bandwidth will be 1 result per cycle coming out at the end, even though you have to wait 10 cycles from the time that one multiply starts till it ends. And all of this, depends on the hardware. So this is one example of pipelining. Here's the other example, which shows up all the time. And all of this is in, I should say, in sequential processors, so that's where we are. And certainly, these are the building blocks for the parallel ones. So almost all the machines now, as I mentioned, have what are called SIMD instructions, single instruction, but they work on multiple data. And so one, in this case, add instruction, if you have 4 words sitting in contiguous registers and 4 other words sitting here, it'll add all 4 at the same time. And it will also do multiplies and divides, and so all of those happen automatically. And the language that's special to Intel is SSE, Streaming SIMD Extensions. That's what Intel calls it. And then they made it longer, so you could do more of them in parallel, and they called that SSE2. And then they changed the acronym to AVX for whatever reason. So they keep growing it from generation to generation. And so now, I think the total length of these registers in Intel machines are 512 bits. So whatever you can pack into 512 bits can happen in parallel. And of course, depending on whether they're single precision or double precision or something else, you can pack different numbers of things into those 512 bits. And so you can have different amounts of parallelism depending on the size of your operands. So, for example, this is SSE2. It's a 16-byte object that can be processed in parallel. That could either be 4 floating point numbers, single precision, or it could be 2 double precision numbers, or you could be doing logic, Boolean operations, ands and ors on bytes, and individual bytes. And you can fit a lot of them in there, 16 of them. And so in one instruction, you can do either 4 floating point operations at a time, or 2 double precision floating point operations, or 16 byte operations at a time. And so if you can get away with shorter precision, which is an interesting question, then you can take advantage of that and go a lot faster. Okay, so what does, and on GPUs, this picture changes, it gets to be thousands of words long. That's what GPUs like to do. So you better be able to find thousands of, vectors of length 1,000 that you need to do. So we'll talk about that later. Okay, so there's some other instructions that are worth knowing about that are special. And part of the floating point standard that everybody implements is this instruction, fused multiply add. So that takes 3 operands, y, c, and z, and in one operation it computes a product and a sum. And it actually does this, can do this in pipeline, and so it's sort of one cycle. Now, why would it do that? So does this look like a familiar operation? Suppose you're computing a dot product, which is an awfully common operation. This is exactly what you're doing. You're taking the product of two vector entries and updating a sum. And so this makes that very, very common operation go a lot faster. And the other thing that most of these hardware implementations do is that it does it in higher precision. So it multiplies these two guys, maybe they're 32 bits. It makes a 64-bit product. It doesn't lose any accuracy. Then it does the sum, and then it rounds. So that's an extra benefit that some people take advantage of to get higher precision results. So in theory, so if you write code and one of your lines of code looks like this, then the hope is that the compiler would say, oh, I can generate one instruction, and it'll run a lot faster. Now, it may be that if you write this code a little bit differently and it's not all just in one line of code, the compiler won't recognize it. And that, unfortunately, is still your problem. So you need to write your code, hopefully, so that the compiler will recognize it can take advantage of that and issue one instruction as opposed to two. And so the compiler needs your help to do this. And there are different optimization flags. So there's -01, -02. Sometimes people discover their code breaks when they use these because the compiler tries to do things that aren't legal or you didn't expect it to do. So it's a little bit of an art. And in fact, there's one compiler flag which I'm going to forbid you to use on the first homework assignment. It's not -03, it's -matmul. And in that case, you're telling the compiler, oh, throw away my code, I'm really doing matrix multiply, and just call the optimized library. Right? That's cheating for the first homework assignment because we're going to ask you to optimize matmul. But it's so common they've thrown that in as an optimization on some compilers. Okay, so that is all I wanted to say about parallelism. Are there any questions before I start diving into matrix multiply and applying these ideas there? Okay. So I'm going to use some simple performance. So I'm going to introduce some simple models so I can abstract away all that stuff that we learned is so complicated. And that we're going to have actually lower bounds on how much communication matmul takes. And we will attain that. And I'm going to warm it up by doing just matrix vector multiply, which is a much simpler thing to analyze. And then I will do matrix multiply. And so, and I will only get partway through this material and we'll finish it next time. So you may ask, why am I optimizing matrix multiply? Because it's the most studied algorithm, I think, ever. And it appears in many linear algebra kernels. It's used all the time. And it's not just, and they use it every 6 months to rank all the 500 fastest computers in the world. So that's another reason to understand it. And it's one of the 7 dwarfs that we talked about before. I'll remind you what those are. And the ideas generalize not just to doing multiplies and adds. It actually generalizes to graph theory. Because if you want to compute all pairs shortest paths in a graph, there's an algorithm called Floyd-Warshall, which you may have studied in a graph theory course. And it's still 3 nested loops, just like matrix multiply is 3 nested loops. But inside, you're not doing multiplies and adds. You're doing things like mins and maxes and sums. But that doesn't matter. I don't care what operations they are. All I care about is how much data I have to move. And as long as it's 3 nested loops, the same lower bound applies, and the same optimizations all apply. So I'm going to tell you these ideas, and we'll be able to apply them to lots of different problems. So just to tell you where this fits into the picture that I had before, here were all of the patterns, the 13 patterns or motifs that are going to come up over and over again. And the 7 that particularly come up in high-performance computing are the 7 dwarfs. And I've circled here the one we're about to talk about now, which is operations on dense matrices, and dense linear algebra in particular. Okay. So let me show you some performance data and then try to figure out where it comes from. And again, this is a little bit of an old machine. So this is the performance of matrix multiply. The horizontal axis is the matrix size, so 100 by 100, 200 by 200, up to 800 by 800. The vertical axis is flops per second, megaflops per second, so up is good. And there's 3 different curves corresponding to 3 different ways of writing the code. The black line is the obvious 3 nested loops that we all learned as sophomores or freshmen, and with the -03 flag, so we're asking the compiler to do as well as it can, and it's getting maybe 20 megaflops. The peak on this machine is 330, so it's getting a very tiny fraction of peak. And in fact, there's a cliff in performance. It does okay for a while, and then it falls off. So what do you think where this cliff happens? Has to do with the cache size, right? So all of a sudden the matrix doesn't fit in fast memory anymore, and it's running terribly. So what about these other two curves up here? The red one is the hand-optimized version, which is a team of programmers at Sun, when it was still Sun, produced. And you can see that's getting up to 300, and then it falls off a little bit, but it's still getting a very large fraction of the 330 peak. And the blue is something called FPAC, which is automatically generated, and it's so written by a code generator which generates many different versions of matrix multiply, and it automatically searches for the best one and picks it for you. So you don't have to do any work anymore, right? And so where did this come from? It actually came from a project here at Berkeley, and it was involved in CS267 a long time ago. And so, and the motivating reason for this was, guess what? Neural nets back in the 90s. It's popular today, and it was popular back then. And the bottleneck for running neural nets is matrix multiply. And so the folks who were involved in doing this decided it was too tedious because they had so many different platforms they wanted to optimize their matrix multiply for. They decided to write a code generator which just generated all the versions I'm about to explain to you automatically, and it just benchmarked them all and picked the fastest one. So it just did brute force search. And that, you can see, does just about as well as the hand-optimized code from Sun. And so so one of the graduate students who was involved in doing that work is named Krista Isanovich, who's now a faculty member here. And I'm pleased to say this just won a Best Paper Prize for a Test of Time award from the conference, because it sort of started the field of auto-tuning and was one of the first results in that. So today, so as I said, this was done around 1995, and since then, for the first homework assignment, where we're going to ask you to tune matrix multiply, some student teams actually build an auto-tuner in 2 weeks. It's gotten easy enough, it's well enough understood that you can just write your own little code generator, and you don't have to do this in homework 1. I'm just mentioning that some teams have done this, and they generate many versions to pick the fastest one. And so you can think about whether you want to write some Python thing to generate that or not. Okay, so now I'm going to tell you where all this performance comes from. And I'm going to start by talking about what a matrix looks like in memory. And I'm going to start with the simplest layouts, but there are going to be a lot more we'll talk about later. So what's a matrix? It's a 2D array. And there's two standard ways to store it, either row-wise or column-wise. And if you're a C programmer, this is what you're used to. And if you're a Fortran programmer, this is what you're used to. There's a mixture of folks out there. And so this is the order of your 5x4 matrix, where I've indexed it as to the addresses in memory. And so when you write a piece of code and you access a sub ij, then the compiler has to do a little bit of work to translate that into an actual location. So it's the address of the initial entry, and then you add if it's in column major order, you add the row index, and then you add the column index times the number of rows, right? So that's how you figure out where you are. So let's but there are other ways to do it too, and we'll talk about those later, but these are the simplest. So now let's suppose that I have a matrix in column major order, and I want to access a row. What's that going to look like? And let me suppose so that I have let's say, a leading dimension, the number of rows, which is, say, 25, but my cache line size is not, is a multiple of 2, right? Because that's what cache line sizes are. Your matrix could be whatever, but it doesn't have to be divisible by the cache line size, right? So what I've colored in here are cache lines. So these are all stored in the same cache line. Those are stored in the same cache line. And that's sort of the mapping of your matrix to the memory. So now, let's suppose that in your code, you say, I want to access that row of the matrix. What is the hardware actually going to do? When it reads in that entry, it's not going to just get that entry. Remember, there's this thing called spatial locality. It's going to fetch that whole cache line. So all those red entries are going to be read in from slow memory to fast memory, whether you want them or not. Then, over here, because it's not lined up perfectly, it's going to get that entry of that cache line. It'll get everybody in that red. And then by the time you've read the whole row in, you've fetched actually all of those funny-shaped red marked cache lines from slow memory to fast memory, which isn't a particularly useful set of things to have read in. And so, but this is going to affect the performance of your matrix multiply if you happen to read a matrix in a row and if the number of rows is not a multiple of the cache line size. So you might think about whether you want to pad your matrix and make it a little bit, have a few more rows which you don't use, but so that the total number of rows is evenly divisible by the cache line size. So instead of having these slanted things, it's all lined up. Okay? So now let me give you the simple model of that we're going to use to, that's going to be much simpler than the pictures that I had before that we're going to have in our heads as we write down code and ask how fast is it. So I'm going to assume we just have 2 levels of memory, fast and slow, and we could extend it to more, but 2 is good enough. And these are the numbers that I'm going to sort of reduce everything to. I'm going to count the number of words moved between fast and slow memory, because that's the most expensive thing. So how many reads and writes between my 2 levels of memory, I'll count that. That's going to depend on my algorithm. I'm going to have a hardware parameter, which is the time per slow memory access, T sub m. You look that up in the hardware manual. I'll count the number of arithmetic operations I do. That depends on the algorithm again. And then I will also look up in the hardware manual the time per arithmetic operation, and it's much, much less than the time to go to fast memory. So, and then the number which I'm going to introduce to sort of measure the quality of my algorithm is this ratio, flops per memory references. That's going to be my metric of success. That's going to determine how fast my algorithm goes. So what is the minimum possible runtime? If everything were in fast memory and I never had to go to slow memory, it would be the number of flops times the time per flop, right? So that's my lower bound. The question is, how close can I get? The actual time in this simple model is going to be the arithmetic time plus the memory time. So flops times time per flop plus memory references times time per memory reference. Let me factor out the lower bound. And I'm left with 1 plus this ratio, times this formula here. So let me look at that. These 2 parameters are ratios of hardware. This just depends on the hardware. Time per memory reference divided by time per flop. Another way you could say that, that's the number of flops you can do in one memory reference. So that's hardware only. This is only depends on your algorithm. It's the reciprocal of this number here. So this number is huge. Remember I said this might be a factor of 100, so that's going to keep me from being close to the lower bound. So I want Q to be as big as possible. I want to do as many arithmetic operations per memory reference as I can, so this factor cancels out that. So in particular, if I want to get, say, within a factor of 2 of the peak speed, that's a reasonable goal, that means that this algorithmic parameter, which I'm going to call the computational intensity, the computational intensity has to be at least as big as that hardware parameter to get half of peak speed. So in that, I'm going to call the machine balance. So these 2 numbers here, the computational intensity has to be at least as big as the machine balance just to get close to the, within half of peak. And so I have these 2 very simple numbers I can compute from my algorithm and from the hardware and ask how close am I going to get. So we'll do this for matrix multiply, but let me warm up with matrix vector multiply and just do the analysis here. So this is, I'm going to multiply a square n by n matrix A times a vector x, 2 nested loops, pretty obvious. And so if I look at the innermost loop, it's computing a dot product. The dot product is the ith row of A and the vector x. So now let me annotate this with what the actual memory movement is. So this is the code that you write. Oops. Let me annotate it. And so let me assume that I can fit a whole row. I can fit x into fast memory, just to keep it simple. So n words fit in fast memory. I can read them in and keep them there. And all the n entries of y fit, so I'm going to read them in and keep them there. And then I'm also going to assume that I can fit a whole row of A. So what am I going to do? I'm going to read in x to fast memory just once, read in y into fast memory just once, and then I'll read A row by row into fast memory, do a dot product. There's no memory traffic in the inner loop, and when I'm done, I'll write y back to slow memory. Right? So that's sort of the simplest thing you could imagine, and it's reasonable to assume I can fit a row into cache. That's not so bad. So what is the total number of slow memory references? I've read x once, I've read y once, and I've written y once, so that's 3 times n. And I've read a once, that's n squared. And that's pretty much a lower bound, right? I've read everything once, and I've written everything that I had to once. So I'm not going to do better than that. How many floating point operations have I done? Well, 2n squared, easy to count. And so the ratio, the computational intensity of that divided by that when n is large is about 2. So 2 is not very large. Remember, it has to be at least 100 in order, let me go back to this picture. So this number here, this q, is 2, and that's not going to, dividing by 2 will not improve this ratio very much. So I'm never going to get close to the peak machine speed. So let me now tell you what that value is of machine balance for a lot of platforms, just to convince you that that matrix vector multiply is always going to be slow. We don't want to use matrix vector multiply. So here's some data from some real machines. And so here I just put in that formula again, which is where I plugged in q equals 2. And so here are a bunch of old platforms. This is data from a former PhD student's thesis. And so here's the clock speed of these machines. Here's the peak megaflop, so that's going to tell me the time per flop. And then he did a whole bunch of experiments to try to compute the memory bandwidth, which is T sub m. And he reported a whole bunch of different numbers here because there's a lot of different benchmarks and they don't all measure it the same way, but I'll just use the minimum to sort of say that's the best possible thing. And then, of course, there's also, depends on, all these machines have different line sizes in the cache, but here's the ratio we care about. This is the time to go to slow memory divided by the time per flop. So another way to say this is that this is how many flops I can do in the time of one memory axis. And these numbers are all much, much bigger than 2. Right? So there's no way I'm ever going to get close to peak for doing matrix vector multiply. So I got to do something else. So I made some simplifying assumptions here, but that's okay. That's we don't want to worry about all those details. So I ignored parallelism between the memory and the processor. Remember, I said the processor could be doing arithmetic at the same time it's going to memory. That would change my model, but instead of adding those two terms, I would just take their max. Right? And, instead of taking the sum of arithmetic time and memory time, if they're overlapped perfectly, it's just the max. That wouldn't change my analysis by more than a factor of 2. So it's okay to do that simplification. I also assumed that I could hold the whole vector x, the whole vector y, and the whole row of a. So that's 3n fit in cache. And that's pretty reasonable size because n isn't usually that big. It covers many applications. It's not good enough for registers. You're usually only like 32 or 64 registers, but L1 is thousands, so that's all right. I also assumed that I only had 2 levels of memory. I assumed there was fast and slow, but you can generalize that to many levels of memory. It's sort of the same story. So that's an okay thing too. So now let me take that model and use it to actually predict the performance and say how close does that really simple model of performance come to the actual measured performance of matrix vector multiply. So let me show you some data. And so the model is just time is flops times time per flop plus memory references times time per memory reference. So that really simple model. And so here is some real data from a whole bunch of different machines. So the horizontal axis is different machines. And the vertical axis is flop, so up is good. And there are 2 models. So the red and the blue are 2 versions of the model, and they're almost the same. It depends on whether I count reading and writing x and y or not. That doesn't change much at all. DGEMV is the acronym for the name of matrix vector multiply. That's the name of the subroutine. And the green is the actual performance, the measured performance. And so you can see that sometimes we underpredicted, sometimes we overpredicted, but it did a pretty good job of saying that we're memory bound. So the model sort of captured that behavior. Okay, so the lesson is don't do matrix vector multiply if you don't absolutely have to. What are we going to do instead? Matrix multiply, and we're going to fix this problem. And so let me start with the naive version and then tell you what the optimized version is. So the naive version is 3 nested loops. And I've drawn a picture of what is happening in the innermost loop. I'm taking the dot product of the ith row of A and the jth column of B and computing C. Okay, so I'm doing 2n cubed flops. And how much data is there? Well, there's A, B, and C. They're all n by n matrices. So the total amount of memory of data access is just 3n squared. And so how big could my reuse possibly be? Well, if I were really lucky, the number of flops, and I only accessed every data entry once, if I were really lucky, the ratio would be growing like n, right? N can be as large as you like, and so I have a great deal of potential here. And for matrix vector multiply, this was 2. For here, it's n. So I'm not going to get to n, but it tells me that there's some potential big speed ups here. So let me annotate this code, this naive code, and say it's awful. We're not going to do it this way. We have to do something much better. So I'm just going to put in some comments as to what actually happens. So I'm going to read in this row of A, and then I notice that the inner loop is going to use this row over and over again, so it's just going to stay in cache. So I only read it once. That's great. So I'm going to read in the row of A just once. That's the lower bound. Then I get into the next loop. That's the row that's the I. Then I get to J. And I'm going to read in C sub ij, which is the thing I'm going to compute. I'm going to read it exactly once. And that's great. I can't do any better than that. Then I need to read in the column of B with which I'm going to take the dot product. And then I do the dot product. So there's no more memory traffic inside the inner loop. And when I'm done, I have finished the entry as C, and I write it back. So I've read A exactly once. Can't do better. Read C once and written C once. So all of that seems wonderful, but what about B? That's where the problem is. So let me count. So I've had to read each column of B n times. Let me come back here. So I read column of B into fast memory. So that's n reads. It's inside these two nested loops. So it's how many times do I read it? It's n times n times n. That's n cubed reads of entries of A, of entries of B. So I have n cubed reads of B, and then the n squared reads and writes of A and C. And so the number of reads is still n cubed. And so my computational intensity is 2n cubed flops divided by n cubed reads. It's still 2. It's still just as bad as matrix vector multiply. And we shouldn't be surprised, because if you look at the two innermost loops here, what are these two? So ignore the I loop. What are the J and K loop doing mathematically? They're taking the ith row of A and multiplying it by the whole matrix B. It's doing a vector matrix product. So it's the same thing as before, and I'm just going to be stuck. So I have to do something differently. And I know I can do something differently. And so the question is, how do I get from there up to there? So here's just another little cartoon about what would happen if we ran this algorithm on a really, really big matrix. And so this was an experiment done by a colleague down at San Diego. And so the horizontal axis is the dimension on a log scale. The vertical axis is the number of cycles per flop on a log scale. And so when the matrix is very small, he's doing at about 16, cycles per flop. That's not terrible. Then there's this cliff, and it goes up to hundreds of cycles per flop. Then there's another cliff, and it actually took him 5 days to multiply a 1,000 by 1,000 matrix. He was willing to do this experiment. I don't know why. And then he actually went up to a 12,000 by 12,000 matrix. He didn't run it very long. He ran it long enough to realize it would take him 1,000 years to finish the code. And the warranty would run out by then. So he didn't finish that particular one. So what was happening here? So if it all fits in cache, or almost, or if you only have a cache miss every 16 iterations, you're down there. If you have a TLB miss and you have to ask, are you in disk or not, every iteration you're there. If you have a page miss and you actually do have to go to disk, you're up there. And if you have a page miss for every entry of the matrix, well, that's the 1,000-year mark. And so, yeah, we have to do better than this. We'd like to be flat down here no matter how big your matrix is. So here's the trick. It's called tiling. And so what I'm going to do is multiply by my matrices not as entry by entry, but block by block. So here's the picture of what happens. So this is no longer a single entry of A. It's a B by B subblock. And I'm going to multiply that by this B by B subblock, get a B by B product, and add it to that B by B submatrix. So I'm going to have 3 nested loops again, but now I'm looping over blocks. And the innermost loop of the algorithm is going to do that matrix multiply and add it to that. So actually, this line of code is a B by B matrix multiply. So there are really 6 nested loops here. I didn't write them all out. So there's 3 outer loops where I loop over all of these blocks, and 3 inner loops where I actually do the work inside the block. And so the idea is I have a parameter here, which is the block size. And I have to choose that in a clever way. And so my code is going to loop over all of the blocks, so capital N. So I have the blocks are B by B, and I have capital N blocks. So I'm going to read in that block, and then in the innermost loop, I'll read that block once, read that block once. So I'm assuming I can fit 3 blocks into cache. And then the innermost 3 loops, no more memory accesses. That all fits inside cache. So let me do the counting and ask. And so I'm assuming that I can choose B so that I can fit 3 B by B blocks into fast memory. So let me do that assumption and then see what happens. So what's the total amount of memory traffic? Then I'm going to read each block of B capital N cubed times. Let me come back here. So how many reads is this? This thing is of size B by B. So that's B squared reads. That's B squared reads. And I'm going to do it capital N times capital N times capital N times. That's how many reads of A, how many reads of B. And so when I do the math, capital N cubed times B squared, that turns into capital N times little n squared. Same, that's reading B, reading A, and I still only read and write C once. So the total amount of, so what is this? Remember, capital N is little n divided by B. So this is B times smaller than it was before. So I've reduced the amount of memory traffic by a factor of B. So that means I can potentially have a speed up of a factor of B when the memory traffic is the bottleneck. So this can be arbitrarily larger than 2, obviously. So the computational intensity, the number of flops per memory reference, is this number B. And so I want to pick B as large as possible. What prevents me from making it infinity, or capital N, or N? I've assumed that all of these blocks, these 3 B by B blocks, have to fit into fast memory. So that tells me that 3 times B squared better be less than the cache size, M sub fast. And so that means the computational intensity is basically the square root of the cache size. And so that tells me that this is how I want to pick B. I want to fill up the cache with these 3 B by B blocks, and that'll make it go as fast as possible. And so if I want to build a computer now that will run at peak machine speed, that tells me, remember, I can compare this computational intensity to the machine balance, which is the time per memory references divided by the time per flop. And I can compare those, and I see that the cache size has to be pretty small, and I can get close to peak machine speed. People happen to build computers with caches that big, right? It's not, a 14 kilobyte cache is not very large. So this tells me I should be able to get to close to peak machine speed on all of these different platforms. So this was one magical algorithm that I told you about, and it turns out that there's a theorem that says this is optimal. And I will have a later lecture in the semester where I sort of say how this has been generalized in all sorts of different ways. But it was originally proven just for classical matrix multiply. And it says that no matter how you organize matrix multiply, no matter what order you do the operations in, not just this clever tiling scheme, then the computational intensity can never get bigger than the square root of the cache size. And so that means that there's a lower bound on how much memory traffic there is. It's lower, so this notation capital omega, that means it's lower bounded by some multiple of the number of flops, n cubed, divided by the square root of the cache size. And so that's going to be our goal for matrix multiply, to go that fast. And you're going to be doing that on your first homework assignment. And so that theorem, when they first proved it, was just for 2 levels of memory. It actually extends to arbitrary levels of memory. It tells you how much memory has to, how much data has to move between L1 and L2, between L2 and L3, between L3 and DRAM. It tells you how to optimize everything. It also works for parallel and sequential code. It tells you how much data has to move between parallel processors. This is just sort of an advertisement for a future lecture. It works not just for matrix multiply, it works for all of linear algebra. It works for Gaussian elimination and eigenvalues and least squares. So, and over the last few years, we've discovered new algorithms for all of those operations which attain these new lower bounds that we'll give you some summary of later. It works not just for dense matrices, it works for sparse matrices. And we recently extended to sort of arbitrary code that looks like nested loops. So there's now a theory that says if you have, and that's a lot of code, right? Nested loops, accessing arrays. We have a lower bound on how much memory traffic that has to use. So there's lots of projects that we can talk about which involve taking these new ideas and trying to optimize other codes. And I better stop. So we'll continue next time.